Hi, my name is Gabriella Silva, and this summer I was working on the sampling distribution of the sample correlation with data that's been subjected to type 2 censoring, and my advisor was Dr. Scott Linder. So in order to understand this project, I want you all to consider the following situation. We have a set of 20 light bulbs, and we've decided prior to the start of the experiment that we're only going to work with 15 of these light bulbs. That is, we're going to wait until 15 of these light bulbs turn off. And so we start the experiment, and once we've started it, we wait for 15 of these light bulbs to die. So in analyzing our data, we're only going to work with the 15 survival rates because we never let those 5 remaining light bulbs actually die. They were always on. So this would be an example of type 2 censoring because the last 5 light bulbs were censored. So type 2 censoring occurs when we have the sample size n, and we've decided that we're going to only keep p of these observations. Censoring is really important because it has a lot of applications in fields such as engineering, geology, biology, and several others. So for this summer, we were concerned with the sampling distribution of R, which is the sample correlation. The sampling distribution is important because it is the probability distribution of R, the sample correlation, based on a random sample. So the reason why we need to know about the sampling distribution is because the sampling distribution allows us to make statistical inference. And so as you can see in these figures here, as the censoring is taking place, the only thing that's changing in these 4 figures is the value of p. So n and rho, the population correlation, are staying the same. And as these are changing, you can see that the sampling distribution is changing as well. So this tells us that censoring has an effect on the sampling distribution of R, the sample correlation. So our next step was try to approximate the sampling distribution. So we want to try to find a curve that goes over the sampling distribution of R and that can be used to predict the sampling distribution of R. The example that we tried to follow was the beta distribution, and the beta distribution basically depends on 2 parameters, alpha and beta, which define its shape. So what we're trying to do is find a curve that goes over this one for some fixed n, p, and rho. So one of the issues that we ran into at the beginning was that the beta distribution actually goes from 0 to 1. However, correlation is defined from -1 to 1. So for that reason, we needed to use a transformation r is equal to 2x minus 1 so that the interval for our distribution would lie between 0 and 1, which is what beta lies between. Then we calculated alpha and beta, and we were actually able to find closed form approximations for alpha and beta using the method of moments. Unfortunately, once we actually tested our results using the chi-square statistic, and information on how to find the chi-square statistic can actually be found on the poster itself, we found that our chi-square statistics showed that the fit was not a very good fit overall. So this basically meant that when rho was very small, so when the population correlation was very low, the chi-square statistics were pretty close to what we expected, so they were close to the expected value of 9. However, as rho continued to increase, the chi-square statistics just grew exponentially, and this showed us that it really was not a good fit, and we probably shouldn't continue going down the same path. However, something that did look pretty promising was that when we were estimating percentiles of the right tail, so that is the 90th, 95th, and 99th percentiles, we found that the approximations we had using R, alpha, and beta values were actually very close to what happened when we simulated these values. So for instance, when n is 30, p is 10, and rho is 0.1, we found that the 95th percentile was 0.8767, and the estimated one was 0.8784, which is very close. Thank you so much to the NSF and to OWU for funding, and thank you so much, Dr. Linder, for the advising this summer.